astronomers find 25 hugely powerful fast radio bursts that keep repeating. Matt Williams' Universe Today reports, like gravitational waves, GWs, and gamma ray bursts, GRBs, fast radio bursts, FRBs, are one of the most powerful and mysterious astronomical phenomena today. These transient events consist of bursts that put out more energy in a millisecond than the sun does in 3 days. While most bursts last mere milliseconds, there have been rare cases where fast radio bursts, FRBs, were found repeating. While astronomers are still unsure what causes them and opinions vary, dedicated observatories and international collaborations have dramatically increased the number of events available for study. A leading observatory in the Canadian Hydrogen Intensity Mapping Experiment CHIME, a next-generation radio telescope located in the Dominion Radio Astrophysical Observatory, DRAO, British Columbia, Canada. Thanks to its large field of view and broad frequency coverage, this telescope is an indispensable tool for detecting FRBs, more than 1,000 sourced to date. Using a new type of algorithm, the CHIME FRB collaboration found evidence of 25 new repeating FRBs in CHIME data that were detected between 2019 and 2021. The CHIME FRB collaboration comprises astronomers and astrophysicists from Canada, the US, Australia, Taiwan, and India. Its partner institutions include DRAO, the Dunlap Institute for Astronomy and Astrophysics, the Perimeter Institute for Theoretical Physics, the Canadian Institute for Theoretical Astrophysics, CETA, the Anton Panenkovic Institute of Astronomy, the National Radio Astronomy Observatory, NRAO, the Institute of Astronomy and Astrophysics, the National Center for Radio Astrophysics, the Tata Institute for Fundamental Research, TFRI for short, and multiple universities and institutes. Now, despite their mysterious nature, FRBs are ubiquitous, and the best estimates indicate that events arrive at Earth roughly 1,000 times a day over the entire sky. None of the theories or models proposed to date can fully explain all the properties of the bursts or the sources. While some are believed to be caused by neutron stars and black holes attributable to the high energy density of their surroundings, others continue to defy classification. Because of this, other theories persist, ranging from pulsars and magnetars to GRBs and extraterrestrial communications as well. CHIME was originally designed to measure the expansion history of the universe with the detection of neutral hydrogen. Roughly 370,000 years after the Big Bang, the universe was permeated by this gas, and the only photons were either the relic radiation from the Big Bang, the cosmic microwave background, CMB, or that released by neutral hydrogen atoms. For this reason, astronomers and cosmologists refer to this period as the Dark Ages, which ended roughly a billion years ago, a billion years after the Big Bang, as the first stars and galaxies began reionizing neutral hydrogen. Specifically, CHIME was designed to detect the wavelength of light that neutral hydrogen absorbs and emits, known as the 21 centimeter hydrogen line. This way, astronomers could measure how fast the universe was expanding during the Dark Ages and make comparisons to later cosmological eras that are observable. However, CHIME has since proven itself to be ideally suited for studying FRBs, fast radio bursts, thanks to its wide field of view and the range of frequencies it covers, 400 to 800 megahertz. This is the purpose of CHIME FRB collaboration, which is to detect and characterize FRBs and trace them back to their sources. As Dunlop postdoctoral fellow and lead author Ziggy Plevnis told Universe Today, each FRB is described by its position in the sky and a quantity known as its dispersion measure, DM. This refers to the time delay from high to low frequencies caused by the burst interaction with material as it travels through space. In a paper released August 2021, the CHIME FRB collaboration presented the first large sample catalog of FRBs containing 536 events detected by CHIME between 2018 and 19, including 62 bursts from 18 previously reported repeated sources. For this latest study, Plevnis and his colleagues relied on a new clustering algorithm that looks for multiple events co-located in the sky with similar DMs. Plevnis said we can measure the fast radio burst sky position and dispersion measure up to a certain precision that depends on the design of the telescope that's being used. The clustering algorithm considers all fast radio bursts that the CHIME telescope has detected and looks for clusters of FRBs that have consistent sky positions and dispersion measurements within the measurement uncertainties. We then do various checks to make sure the bursts in a cluster are really coming from the same sources. Of the over 1,000 fast radio bursts detected to date, only 29 were identified as repeating in nature. What's more, virtually all repeating FRBs were found to be repeating in irregular ways. The only exception is FRB 180916, discovered by researchers at CHIME in 2018 and reported in 2020, which pulses every 16.35 days. With the map of this new algorithm, the CHIME FRB collaboration detected 25 new repeating sources, almost doubling the number available for study. In addition, the team noted some very interesting features that could provide insight into their causes and characteristics. As Plevnis said, when we carefully count all of our fast radio bursts and the sources that repeat, we find that only about 2.6% of all fast radio bursts that we discover repeat. For many of the new sources we have detected, only a few bursts which make the sources quite inactive, almost as inactive as the sources that we have only seen once. We thus cannot rule out that the sources for which we have so far only seen one burst will eventually show repeat bursts as well. It is possible that all fast radio bursts or sources eventually repeat, but that many sources are not very active. Any explanation for fast radio bursts should also be able to explain why some sources are hyperactive while others are mostly quiet. These findings could help inform future surveys, which will benefit from next generation radio telescopes that will become operational in the coming years. These include the Square Kilometre Array Observatory SCAO, which is expected to gather its first light by 2027. Located in Australia, this 128-dish telescope will merge with the Meerkat Array in South Africa to create the world's largest radio telescope. In the meantime, the prodigious rate at which the new FRBs are being detected, including repeating events, could mean that radio astronomers could be close to a breakthrough. This article was originally published in Universe Today by Matt Williams, and it's on Science Alert. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box.